Now, here's a real example of a rate mechanism. We have a reaction that takes place in two steps. Step one is where molecules of NO2 hit molecules of NO2 and they end up making NO3 and NO. This step apparently is a lot slower than the second step. In the second step, molecules of NO3 and molecules of carbon monoxide hit each other and they make NO2 and CO2, and that is very, very fast. Now, the interesting thing is that when you put these two reactions together, the first step leads into the second step. This down below is the overall chemical reaction, where NO2 molecule, a single NO2 molecule, and carbon monoxide molecules hit, and they make NO and CO2. Notice that molecules of NO3 have completely disappeared. They're actually called intermediates. They're compounds that are produced from the first reaction and then consumed in the second reaction, so that very mysteriously, they don't really appear in the overall chemical reaction. Now, since the first step is the slowest step of the sequence, this is called the rate determining step. And the point for rate mechanisms is that the rate of the slow step is so much slower than the rate of the fast step that the rate of the slow step pretty much determines the overall speed of the chemical reaction. In other words, step one might have a rate of 10, really, really slow, like 1 mole per hour. Step two might have a rate of 100 moles per hour. Well, that means that the fastest this reaction could ever proceed would be 1 mole per hour. The first one would limit the speed of the overall reaction. The second one doesn't really matter because it's so fast. Now, what this means is since the rate for the first step pretty much determines the rate for the overall reaction, that means the rate law for the first step pretty much determines the rate law for the overall reaction. And for the rate mechanism steps, the rate law is equal to the stoichiometry of the reaction. And so the rate law for step one would be the rate for step number one would equal K for step number one times a molecule of NO2 hitting another molecule of NO2. And so that means that this reaction would be second order with respect to NO2. It doesn't really matter what the concentration of carbon monoxide is. Carbon monoxide is not important in the overall order. So since this is the rate law for step number one, and since step number one is the rate determining step, this is the rate law for the overall reaction. Here's another quick reaction where N2O is making N2 and O in step number one, and then in step number two, the oxygen atom that's created reacts with N2O and makes N2 an oxygen gas. So the overall process looks like there's going to be two molecules of N2O that end up making oxygen gas and two molecules of N2. Now the question is, what's the rate law for this? Well, since the first step is the slow step, this is the rate determining step. So therefore, the speed of this reaction pretty much determines the speed of the overall reaction down here. So the rate law is basically, for this overall reaction, is basically the rate law for the first step. And so the first step pretty much is determined by the concentration of N2O. So the rate law for the first step would equal the K for the first step times the concentration of N2O raised to the first power. And this is also the rate law for the overall reaction.